Good afternoon, everyone. Okay, so this is our finals week. We have 2 more classes. We will have to do fluids for these 2 classes. But that being said, this is relatively short amount of time. So like I said, for gravitation, simple harmonic motion, and fluids, they're relatively less problem solving, but mostly has to do with the questions are relatively simpler, more of a plug and chug or conceptual questions. So even though there's a lot of content, but also knowing that the level of requirement for these contents are relatively lower than the other topics, such as conservation of energy, momentum, angular momentum, and torque notation. Those are topics that you would expect to have longer problems to solve. Also, pay attention to that so you can budget your time wisely when you're preparing for your final exam. So the final exam again is going to be on the Tuesday. This is sent out on your Blackboard announcements next week. So time is really coming up. I hope that you are actively preparing for the final is coming up next week. So it will be 3-hour period and within 24 hours duration on Tuesday. And the content is cumulative in the sense that you still need to know how to use Newton's second law, right? You still need to know what conservation of energy is, but the problems are mostly in the context of what we covered after the second term. So starting from rotational kinematics to fluids, which will be the end of this week. Okay, so there are 25 questions total, and there's a practice exam on Blackboard. Okay, all right. So my office hours are Wednesday from 12:45 to 1:45. Thursday from 11 to 12. I also added an extra office hours on Friday. That's for my other class. We used to do recitation, but I changed to an office hour format. So I'm going to send the link for that office hours to you guys. You're welcome to come on Friday as well. So whoever is there wanting to get help, you can come Friday from 12 to 2. That I will send out an announcement on Blackboard again. Okay, just want to make sure that you have the opportunities to ask questions before the final. And yeah, so for Tuesday of the final, I could open up my class Zoom, just like what we did in the past. If you run into a burning question last minute, you can come ask me. So next Tuesday. So yeah, I could do that. Okay, but I want you to do your bulk of work before the date comes. Don't wait until last minute. All right. All right, let's start with our topic. With density, with fluids, there are a lot of, it's really hard. I'm using my slides because I can animate a lot of this information. I may, when I need to write, go back to my tablet. So there may be a little bit transition back and forth. But so far, I'm using my slides for now on my computer. So I couldn't write, but I can change it to a tablet later. Okay, so first of all, we will need to define some concepts before we discuss fluids. And then again, we'll talk about what is fluids later. First thing we discuss is the density of fluid, or it's the density of any property, solids or fluids. It's an intrinsic property of a material, and we use a Greek letter rho to represent it, right? And you probably already know this. The density is defined to be mass over volume. So you have some material that's homogeneous, meaning that everywhere across the material, it's made the same way. It's not like you have part is more dense than the other, then you cannot calculate density this way, right? But if it's homogeneous everywhere, then you can use the overall mass of the material divided by the overall volume. That gives you the density. And you can see the unit for density would be mass over volume would be kilograms over meter cubed if you're doing SI units, or you can use grams or per centimeters cubed for the density, but they're not equal. because if you do the calculation, 1 kilogram per 1 kilograms is 1,000 grams, but 1 meter cube is not 1,000 centimeter cube, right? 1 meter cube is how many centimeter cube? 1 meter is how many centimeters? 1 meter is 100 centimeters. So it's 100 to the power of 3. It's going to be 10 to the 6, a million centimeter cube. So 1 kilo per meter cube would be 10 to the negative 3 grams per centimeter cube. Or in other words, 1 gram per centimeter cube is 1,000 kilo per meter cube. But if you use kilo, we usually do kilo per meter cube. We don't do kilo per centimeter cube. If you do grams, you do grams per centimeter cube, not to mix and match. That's just the convention that people tend to use. This is a unit for density. So now let's talk about fluids. There are 2 types of fluids. One is the gas. One is your liquid. They're all called fluids. So fluids is different from solid materials because fluids are able to flow and solid is not able to flow. No matter if you're talking about gas, they're free to flow, of course, right? Air can come from here to there. If you're talking about liquid, water can flow. It can flow from here to here. But if you're talking about solid materials, that they cannot flow. For gas is a bunch of molecules flying about. Occasionally they collide with other molecules or they collide with the materials around them, like the wall or any other object in the gas molecules in the air. Because there's a lot of space between these molecules, you can see gas is compressible. You can easily expand some volume gas or compress it. However, another type of fluids are the liquids. Even though they're not as rigid as a solid material in the sense that they can flow, but there are very much less gaps between these molecules, so they cannot be compressed like the gas. You cannot compress or expand the liquid. It's incompressible because molecules are very close together. And we combine the liquid and gas all together, we call them fluids. So when you're studying fluid dynamics or fluid statistics, these are considered, statics are considered all fluids considered liquids and gases altogether. There's another concept that we use to help us understand fluids other than the density, which is a basic property of all matters. We also talk about pressure when we're talking about fluids. This is not a strange concept. We have all encountered that in our daily language, or probably even use the physical terms. Now, for example, when we are sitting in the airplane, right, or on the water, you'll feel it in your eardrums that there is an imbalance of pressure. Sometimes during the takeoff of or a landing, you'll feel that in your membranes of the ear because there is an imbalance of pressure on one side or the other, and feel uncomfortable until it pops in the sense that the pressure matches up and you feel normal again. So we know about pressure, and the pressure comes from, you probably know, is the air outside of your eardrum. Because we are living on Earth, right? So we are all are immersed in the atmosphere pressure. We have a lot of, the Earth has a big layer of atmosphere, so these air are exerting a pressure on us. And sometimes you see this in weather reports when they talk about the pressure. When the pressure changes, you have low pressure associated with a stormy day, and you can feel it, you feel really uncomfortable. There's also, we talk about air pressure in our car, tires, bicycle tires. There's not enough pressure in it. You wanted to pump some air, right? Your recommended tire pressure is kept, for example, with 32 psi, and we'll talk about what that means later. That talks about how much pressure, how much air do you want in your tires. Of course, you can see that if you have poked some holes in the can, the water pressure will force the water stream out of the holes, and the pressure of the liquid associated with the liquid, not just the gas molecules. So we can define pressure by looking at how much force exerted on the wall around the liquid or gas molecules. So pressure, you can see that if you have a much larger area, then there's much force. The fluid will exert a force on the walls of the container. We define pressure to be force over area. So it's the force per unit area, that is the pressure. So you can see that for example, you can, if you take a needle, right, a very sharp, pointy needle, and you kind of poke your skin, even if you use very little force, you can see that it will exert a lot of pressure. You gotta be very careful because the area is so small. All the force is concentrated on the tip of the needle, so you have a big pressure. On the other hand, if you have a flat surface, and you can exert a lot of force on it, you can press it against your arm, but your arm will not be harmed because all of that force exerted over a bigger area and there's a very small pressure, right? You can see that pressure is dependent on both the force that you exerted as well as the area that is exerted on. Pressure is a scalar. It doesn't really have a direction. Okay, we don't really say the pressure is to the left-hand side. That's not how we say it. It's just a scalar. And we are saying, looking at the force on the area is perpendicular to this area. The SI unit for pressure is Pascal. 1 Pascal, 1 PA is 1 Newton per meter squared. If you plug in the SI unit for force as well as the SI unit for area, you get Newton per meter squared. That's 1 Pascal. When you're talking about the pressure in the gas, the gas molecules, where did the pressure come from? We're saying pressure is force per unit area. How would a gas molecule exert a force? They exert a force because they're constantly colliding with the wall or colliding with an object you put inside the room, right? So that way they exert a force and give you the pressure. Of course, the more area a wall has, the more collision it will endure, and there's more force and there's more pressure. As we talked about, pressure is related to force and area. Okay, there's a question. Pascal is Newton meter to the power of -2. Yes, so Newton per meter squared, which is Newton times meter to the power of -2. Yes. So when you're in a room, right, there is pressure of all these gas molecules all around us. They're constantly pressure have a collision with the wall. But with any other object in it, it's also have a collision with any other object in it. If you have a table right here, they're hitting the table, they're exerting the pressure on all sides of the table. You have a computer here, they're exerting pressure on all sides of the computer. And you have a human being here, and there's gas molecules are exerting pressure all over you on your body as well, right? So it's not just the wall. But at the same time, when you have air from one side pushing it, you have air from the other side. That's why you don't see these objects are moving, because the net force is 0. So the Pascal is actually, the SI unit is a very, very small quantity, very small unit, in the sense what we deal with in our everyday life. We usually use a different unit, that is 1 APM, 1 atmosphere pressure. That is the pressure of the air we measure at sea level. Obviously, that when you measure at sea level, or if you go higher up in the sky, you'll see different pressures, but we define 1 ATM to be what measured at the sea level. And it's at 101,300 Pascal. So Pascal is a smaller unit. When we're dealing with everyday language, when we need to talk about what is going on in the atmosphere, we need to use 1 ATM. The atmosphere pressure, ATM, that's the synonym for atmosphere pressure. Not only for our gas, there's pressure in the liquid. So here, you're gonna see what happens in the liquid. You see a container, right, with some liquid in it. And we highlight this blue little column. This is still also just water, but we are going to focus on analyzing just that column of water. This column water has a depth of D and a cross-section area of A, right? This is in the container of filled with water. So if we consider this little column of water, we are going to do a force, draw a free body diagram on this column of water because it is not moving, which means all the forces acting on this column of water must be balanced. So let's see what is exerted on this mass. First of all, you have the water, the top surface is exposed in air. You have air constantly pushing. So you must have the air pushing down. That is a pressure exerting on the surface of water, pushing down, right? So the amount of force from the air is pressure times area, right? So it will be atmosphere pressure P times area A. So P times A is a force pushing down on the water. And this little column also has its own weight. So there's your gravity mg also pointing downward. And you can see they're all balanced, right? They are balanced. So there must be pressure that exerting on this column of water by pointing upward, okay? When we say the pressure exerted all around, right? So if you look at this column at the bottom of the blue bar, the bottom surface, you have other liquid around it. So it's going to exert a pressure to the bottom of the blue column that is pressing upward, pushing up, because pressure is from all different directions. So this pressure P times the area will be the force that is balancing both gravity and the atmosphere pressure of the force. So P times A balance on mg and rho times A. So if we write our force equation, that these forces are equal. So PA is equal to P naught A plus mg. So we are replacing mass with density times volume. As we said, density is defined as mass over volume, right? So mass is density times volume. And the volume of this blue column is what? Area times depth D. So mass becomes rho times A times D. So you can plug that in mg, you get P times A is equal to P naught A plus rho times A times D times G. You have A on all the sides, you can cancel out A. So you can see we've calculated the pressure underwater, P at a particular depth underwater is P naught plus rho G times D. Okay, so this is the pressure you feel at a depth D underneath the surface of the water. Not only you have pressure, atmosphere pressure P naught, you also feel the pressure from the water above you, which is rho times G times D, right? Which makes sense. If you're at the surface of the water, what do you feel? You feel the pressure from the air only. When you go under the water, not only you feel the air pushing you, you still feel all the water above you that is have the weight of the water that is creating another pressure. So putting those two together, you get the pressure at a distance D under the surface of the liquid. As you go further and further deep into the ocean, right, that there are more and more liquid above you, and there's more and more of a pressure that you feel. So there is only so far you can go down in order to be safe, because you don't want it to continue to increase the amount of pressure that you feel around you. Because this pressure will increase as you go deeper. Okay, so this is a checkpoint question you have already done. We're looking at the body of water, and A and B are 2 points of the same depth. We're asking that how do they compare? How do the pressure compare? So you can see that we have just talked about how to calculate pressure on the water is P naught plus rho times G times D, right? A and B are at a same depth from the surface of the water. Because they are at the same height, they're at the same depth, they're going to give you the same pressure. No matter if you're diving at point A or diving at point B, you're going to feel the same pressure. That is not going to change just because you have a boat floating above the point A. That is not relevant. All you cares is what is the height above you? What is the height of the water above you? Okay. So if you did not have the boat in it, obviously pressure A and B would drop. You have the boat in it, you can see we transfer that influence into, when you put the boat in it, the overall water level will rise, causing that depth to be deeper and give you a higher pressure. But in this case, A and B both experience that rise of the water, right? They both have an increase in the depth. So what you care right now is the distance from the surface of water to the point you're interested in. Right now, the A and B have the same depth, so they have the same pressure, right? And it's B was the correct answer. So continue to talk about atmosphere pressure. Of course, we have our air molecules exerting pressure on all the objects around you, including yourself. We have the air pressure on us right now. And if you're curious about what is the pressure, we have already talked about 1 atmosphere pressure is about 100,000 Pascal, right? So you can change that to something we're more familiar with in terms of pounds and inches. That's the everyday unit that we use in our daily lives. That's about 15 pounds per inch square. So about a 1 inch square on your body, every little square inch, you are feeling 15 pounds of force. That is quite a lot of pressure. Let's do an example. If we have make a sphere with 0.1 meter radius, then we can calculate the amount of pressure exerting on the sphere, given the surface area of the ball is 4 pi r squared. And we can easily calculate how much force it's exerting on this little ball. That's really a lot, over 2,500 pounds, right? So it's but we don't really feel it in our everyday life. But if you want to be able to see just how much force that is, there is a famous experiment people did in history. I found a video. We have this demo in our demo room, but we can't do it. So we can look at this demo online. Is demonstrating how large of such a force there is. Now, in our daily lives, you take a ball, right? You have air outside, you have air inside. You're not going to see the pressure. But what we're doing is let's suck air out from the inside. So you're only having the air from outside. So the air from the outside are going to push in the ball so that the ball is made of 2 hemispheres, and they're pushing in so hard that you cannot drag them apart. So I'm just showing just how big this air pressure is. So let's take a look at this demo together. 1 second, let me change the screen to what I'm seeing. Okay, 1 second. Are you seeing the demo now? Can you see it?
Yes.
Oh, good.
Yes, yeah.
Okay, so what they're doing is you can see the two hemispheres, they're going to connect this to a tube and suck the air from the inside. So create a vacuum within. So inside no air, only the air is outside. So they're sucking air out of the ball. And you can see the pressure shows decrease. Okay, and then they get rid of the tube, and so they close it off, and they're trying to pull it apart. You can see that 2 people cannot pull it apart. Probably not even 10 people cannot pull it apart. In history, you can use 2 horses. Not even sure if they can pull it apart, because you can see the amount of pressure on it right now is 2,500 pounds. That's a lot of force. They let a little air in and just see how easy it is to get the two sphere to disconnect, because right now you have air from both inside and outside. Of course, now it is easy to pull it apart, right? So this is just a demo to show the atmosphere pressure is real, even though we don't feel it in our everyday life. And thank God we don't feel it, right? Because if we are like the ball, if we feel it, that's going to crush us. So how come we don't feel it? If we have 25 or more than 2,500 pounds on us, because we have overall a bigger surface area than the ball, how come we don't feel it? If air are pressing on us from all sides, shouldn't we be crushed already?
Do the fluids in our body exert an equal pressure?
Yes, so we are not a vacuum. We have air within our body as well. We have maintained a balance of internal pressure outside. That's why it does not do anything to us. Most of the time when we feel an imbalance of the pressure is actually when the atmosphere from the outside changes. You go high in the mountains, the air pressure drops, and you feel that a little bit imbalance. But yeah, because we always have that air inside our body, so we do not feel the pressure. Only when you are having a vacuum with it, then you're going to feel the pressure from outside. Okay, so here is a question. We have a 55-gallon of drum. What if we evacuate all the air from inside? What will happen to this gallon drum? Go ahead and let you vote on this. Just, I think intuitively it makes sense. I don't think this is a tricky question. Cool, you saw someone who tried to demonstrate it. Yeah, get a vacuum seal is really tricky. We tried to do the demo with the hemisphere. We tried to do it in class in the past, but we couldn't get a good vacuum and didn't work. It would be great if it could work though. You boiled water in the drum and then put it in liquid nitrogen. Okay, so this is more than, I think more than what we are trying to demonstrate. Not only you're taking air out, you also are rapidly freezing your water, right? Making really cold. So I think that's a really interesting. I think that will show you something else, because when you put water in liquid nitrogen, you're fast freezing it, and your water will become ice, and that has to do with, oh, just to condense it. I see. So what happened eventually? I see. So did you fill the water all the way up to the top of your drum, leaving no air inside? I see. Okay, very cool. Thank you for sharing that with us. Okay, let's go back to our question. If you guys, couple more seconds if you haven't put in your vote already. All right, let's take a look. I'm going to end the poll, okay? All right, so what happens if you are able to create a vacuum and suck the air out of the, evacuated out of the drum? We agree that majority said it's squashed like stepping on the soda can, right? All right. Okay, so B would say squashed like stepping on the soda can, meaning it will be squished this way, but it will not be squished on the sides, only on this way, but not the other way. So that's the difference between B and C. Whether it's going to be feeling a pressure only this direction or feeling pressure all around. So that is the difference, okay, between B and C. So we all agree it's going to feel the pressure from outside of the can, from the air around it. So it's going to implode rather than explode. That we agree. But the question is whether it be straight down or from all sides. We can do a quick calculation for the atmosphere pressure if we use PSI. So what PSI, that is a unit you have for your tire, right? 32 PSI. That is pound per square inch. So that is a unit. So if we use 14.7 pound per square inch, and if you calculate the area on the top of the drum, you can calculate the force, right? It's a lot of forces. Pi r squared is the top and the bottom surface. For top and bottom surface, you're going to feel 6,600 pounds. Of course, you feel the force from the side and the bottom as well, right? The side of the barrel will be 2 pi r times h. That is the surface area, and you can see it's going to feel a lot of force from the sides as well. So when the air is removed, you feel the force from all around, which means it will crush the soda can from all sides, not just from the top, right? From all sides. So that's just a very subtle point to show atmosphere pressure pointing in all areas. A lot of times we are talking about air using the height of the mercury. So this is related to another way of we discuss pressure. So we can fill a tube, flip a tube filled with mercury upside down and put it in a bucket of mercury. And you can see that there is a height of the mercury column will remain in this tube. We can examine the pressure at this dotted line shown right here. Outside of the tube, you have the atmosphere pressure only, right, which is P naught. And because you can see the column of the tube in the static equilibrium, which means you will say, why wouldn't this column of water or mercury fill out, right? It has weight, it shouldn't go down, but there's something that is supporting the weight of the mercury. That is the atmosphere pressure, right? What the atmosphere pressure is trying to push it in. So in the sense that is supporting the column of the mercury. So it's balancing the weight of the mercury. The weight is another way to talk about that is the pressure from the hydrostatic pressure of the mercury is rho times G times H. Rho is the density of mercury, g is gravitational acceleration, little g, and h is the height. Okay. These two must equal, right? This is coming from the force balance. The force from the atmosphere pressure pointing up, that is P naught times A, pressure times area, that's the force. The gravity pointing down, that is rho GH times A, that is mg. M becomes rho G, N becomes rho H and A, okay? So rho GH times A is equal to P naught A, because the area is the same area. So a lot of times instead of writing a force equation, we write a pressure equation. The pressure has to be equal because the area is the same. We can cancel it from two sides of the equation. So P naught is equal to rho GH. So another way to represent how much pressure, for example, you want to say 1 atmosphere pressure, and how high the mercury could it support, right? So we simply use the amount of mercury it can hold up in the column to talk about the atmosphere pressure. So 1 atmosphere pressure could hold 76 centimeters or 760 millimeters of mercury. A lot of times we do 760 mercury as the same measurement for 1 atmosphere pressure, right? You see that being used in medical systems when they measure your blood pressure or something like that. You probably have seen this kind of a unit before. Another thing, if you look at this column of mercury being supported, there's a little gap from the bottom of the tube to the surface of mercury, right? Little gap. That's the vacuum. So you can see that the mercury goes up that high is not because the vacuum sucked it up, but by creating a vacuum, you're allowing the atmosphere, you're allowing the air on our other side to push. So instead of it sucking, you think, okay, it's because I sucked up the air, the vacuum sucked the water or the mercury up, but it's instead of that, it's the atmosphere is pushing the water or the mercury up. So we need to know the mechanism behind this. You can measure the atmosphere pressure if you use a different material. Instead of using mercury, you use water. You can see that will support different height of water. It turned out 1 ATM can support 10 meters of water. That's about 33 feet. Whereas for mercury, it can only support 30 inches of mercury because mercury is a much denser, has a much bigger density than water. Rho is much bigger, so the height will be much smaller. So here's a clicker question. Let's say you have a super long straw. And you have a straw that's more than 40 feet and try to drink water from 40 feet above the ground to drink the glass of water. Would you be able to make it? I'll let you discuss it for a minute or two, and then when you come back, we can vote. Okay? All right, 2 more seconds on this question. Okay, I'm gonna go ahead and end the poll. We're pretty much tied between whether you can do it or not. You just have to suck hard enough, or maybe it wouldn't work no matter how hard you try. So can anybody tell us, first of all, anybody would like to share, what is the mechanism behind using a straw to drink water using a straw? We have all done that before, right? So what is the mechanism of being able to have the water drink in the glass, but then the flow into your mouth? What is the physics behind it? Even babies can figure out using a straw to drink water. But I think we'll be able to answer more than that is if you suck, you get liquid in your mouth, but why? Yeah, so Tana said, removing air from above the water, by removing air in the straw, you have created a vacuum. Maybe it doesn't have to airtight, maybe it doesn't have to be 100%, but you have lowered the atmosphere pressure inside the straw enough so that the atmosphere pressure around your glass of water is pushing the water in. So it's constantly pushing it above the straw. Now the water has a place to flow from higher pressure to low pressure because you got a more force pushing it to the other side. Very good. So when we're sucking, what it's doing is removing air. Okay. So how does that relate to, is there a limit of how high of the straw we can use? Let's say this person is very good at removing air and creating a perfect vacuum inside the straw. Do you think that atmosphere pressure could push up the water all the way up to 40 feet? If it could, then he or she can get water. If the pressure couldn't, then they're not gonna get water. Do you think the atmosphere pressure can push water up to 40 feet? Yes.
No,
No, and why not?
because it can only go to 33.
Yes, because we said 1 atmosphere pressure can support 33 feet of water. And you can see that in the previous slide, it is, I'm sorry, I went too far. It's 33 feet of water. That's how much it can support. It cannot support more than that. At 30 inches of mercury, right? So if you wanted to make it go higher up than 33 feet, it's not gonna happen, no matter how hard you try. The answer would be no, it cannot work, right? So be very careful, it's not what you're doing, it's not sucking the liquid in, it's really, you're allowing the atmosphere to push the liquid out. All right. Here, let's continue to look at pressure of the liquid. So a lot of times you have different places inside a container that are connected, right? And For example, here you have sort of two containers and they're connected in the bottom. Anywhere in the connected static uniform density fluid, the pressure at a given height is always the same because they're connected. You cannot increase the pressure at one place without increasing at the same time in another place. What I mean by that, if you push it in on one side, the other side will be, the water will rise up on the other side as well. So the pressure throughout the liquid are all increasing because they are connected. This is the Pascal's law. A pressure change at one point in an incompressible fluid is incompressible, right? Because if you pressure one place in, it cannot be pressured, cannot be compressed, it can only go somewhere else. So giving the other side a rise in the height. So that change, pressure change, appears undiminished in all points in the fluid. So for example, right now you're looking at the first dashed line, you have atmosphere pressure only, P naught, from just the air. At a distance d below, you have another pressure from the water, which is rho g times d. If it's water, you use the density of the water. If it's some other liquid, you use the rho, the density of another liquid. But anyway, it's rho times g times d. Let's say you pressure down, you put some force down in the left-hand side, okay? You have a piston, you really pressure it down. So what will happen is the water level from the right-hand side rises, okay? And you can see that right now, if we were to write our pressure at the surface, is no longer just P naught. At the piston is P naught, and also you have this extra force. So it's P naught plus F over A right at the surface of the water level on the left column, on the left-hand side, right? So, and then you can look at what is happening at the bottom. At the bottom is at a distance d1, which means you have to add whatever it is at the surface by rho times g times d1. So it's P naught plus F over A plus rho g d1. Okay, and that has to equal the pressure on the right-hand side. If 2 points at the same depth, they're going to have the same pressure, right? So let me get this out of the way. You look at the right-hand side of the dashed line, it's at a distance d2 below the water level. So which means the pressure over there is P naught, the atmosphere pressure, and liquid from the right-hand side, which is rho g d2. And because they're at the same level, the third dashed line, they should have the same amount of pressure. These two has to be equal. So the P here is the same as P here. These two are equal. This one is equal to that one, okay? So you can see that by putting this force in, you can say, okay, if I exert 100 pounds, how much the water level will rise? You can set them to equal, and you can kind of calculate how much D2 has to be in order for them, in order to eventually have a static equilibrium. Oh, right. All right, so here we have a question related to what we are seeing. You have that container just to receive the left and the right. And you imagine you have two piston that you have a person standing on the left and you have a big car sitting on top of the other. They're both pressing down on the liquid. Okay, so we know the mass of the person, 60 kilos. And we know the mass of the car, 6,000 kilograms. So how much bigger is the area between the left-hand side versus the right-hand side? So the right-hand side has a much bigger area, the left-hand side has a smaller area. How do we, how much bigger? How many times bigger? Okay, so if you start writing down the expression on the dotted line, you're able to find out the relationship of the area comparing one to another. Okay, I'm going to give you at the end a couple minutes to discuss this. After you come back, we can vote on this. All right, let's vote for 10 more seconds. We will close the vote. All right, any last minute vote? Okay, I'm gonna close this. All right, you can see that the mass of the car is 100 times of the mass of the person. Does that also translate to the air? The area is also going to be 100 times. Ah, very good. Indeed, it is going to be that same proportion. How do we figure it out? We're going to look at the pressure of the same at the same height. So here at the dotted line area, we're not looking at anything below the water, just at the same level of the surface of the water. You have pressure from the left-hand side. There come from two different sources. One is the atmospheric pressure, as always, the P naught. Another, you have a person standing on it. So the weight of the person will exert the pressure on the left-hand side, right? You have to divide the force by the area to get the pressure, right? The right-hand side, you have the exact same thing, P naught, but instead you have the weight of the car exert a force over a bigger area, so F over R. Now, the two sides are at the same height, so they must be having the same pressure. So you can set the pressure from the left equal to the pressure from the right, okay? And you can say they both have P naught, that cancels out. So F from the left over the area of the left equals F from the right over the area of the right? So that the area of the right is 100 times more, 100 times of the area of the left. So the same proportion. Yes, you have a much heavier object, but the heavy object is spreading out the force over 100 times larger the area. So the effect of that is the same, having the same pressure exerted on both sides. Okay, yes, C is correct, very good. Okay, so here comes our, we talked about Pascal's law, right? What is Pascal's law? Saying that if you have an increase in one area of the liquid, incompressible liquid, you're causing the pressure to increase in all the other areas. So if you push down on one side, it's not like you're only increasing pressure here. Water level will rise up other places, and the pressure will also increase in other places of the liquid. Now we also have another principle called Archimedes principle. This one is very famous. This one I'm sure that you probably have already heard about. So what does Archimedes principle tell us? And since our labs this lab happened sooner than our lecture, so you probably have done this lab already. So you probably have heard about this. A body partially or fully immersed in the liquid will feel an upward force that is equal to the weight of the liquid displaced. And that is called the buoyant force. It's a force that makes you an object afloat, supporting the object. So it is equal, the amount of force equal to the weight of the liquid displaced. Because when you put something in water or the liquid, you are displacing some liquid, right? Because the liquid has to go somewhere else to make space from the object. So it's equal to the water that's being pushed away. Let's say you have whatever amount of water being pushed away, 1,000 milliliters, 1 liter, we're talking about volume. So if you have the object has this much volume, has let's just say 2 gallons, for example, that's a volume. And when you put it fully immersed in water, the water has to make space for the object for 2 gallons, right? So 2 gallons of water will be pushed away, will be displaced. So what is the weight of those water? Well, you use the density of the water multiplied by the volume of the water, that is becoming the mass of the water. If you use mass times G, you get the weight of the water. So the weight of the water that's been pushed away is rho, density of the water or the fluid, times the volume of the water being displaced. If it's fully immersed, it's going to equal to the volume of the object, or if your object is half in water, then it's only half of the liquid. It is rho times V times G. That is the amount of the buoyant force that you're feeling. Now, if you're fully immersed, these volume are equal. If you are half partially immersed, the volume of the liquid is going to be smaller than the actual volume of the object, because part of the object is still in air, it's not in the water. So for example, if we have an object and we hold it on a scale, right? We can measure it in air, or you can dip it in water. We can dip it halfway in water, or you can put it 100% in water. So what do you think we will measure in each of the cases? Let's talk about this before I show the solution. For scenario one, the first one, you're just holding the object in air. What do you think the scale will read? You don't have to tell me the final answer. You can only say, okay, how would I calculate the measured weight? What it would be? Would just be object, the weight of the object, right? And that would be density of the object times volume of the object. Okay? So for case one, you will have density of the object is 8 grams per centimeter cube times the total density, the density times total volume of the cube. It's a cube, so it's 8 centimeter cube, becomes 64 grams. So that is a mass. You're going to measure mass times G. You're going to measure that amount of force. That's your weight. When you're that is out of the water, right? So you're going to measure 64 grams of mass times little g. You're going to measure 0.464 newtons. So that's what's reading on your scale. And you can put it in the water. So when you put it in the water, are you going to measure a number bigger than when you measure it out of the water, or smaller, or the same? You put the object in water and you read the scale. Are you going to read exact 0.864 newtons, or something bigger or smaller?
Smaller than 0.64 newtons.
Yes, because yes, very good. Because now you have the buoyant force acting on the object, try to lift it up. So you have FB, and we know how to calculate FB because the amount of force it feels is equal to the weight of the water displaced. So we can just calculate the FB. So use density of the water times the volume of the object, which is the volume of the water, because the object is now 100% in the water, times little g. You have 0.08 newtons. So you are going to measure something 0.64 minus 0.08 newtons. That is your measured weight. That's much smaller. Now, if you put it halfway in the water, the buoyant force is going to be half what you had, because now your immersed area is only half. The displacement of the water is less. So FB is now 0.04, it's half. And you measure the weight will be 0.04 more than that. Okay, so it's 0.6 newtons, 0.04 less than in the air, but 0.04 more than your 100% in water. Okay. Okay, so this one is a very good checkpoint question you have already done. So let's see if we need to spend a little more time on this. We have an ice cube is floating in a glass of water. As the ice cube melts, what happens to the level of the water? So you guys have already done this. And after what we discussed so far, what do you think about this question? What do you think about the level of the water? Will it rise or fall, or will it stay the same?
It will stay the same
Okay, and why is that?
because when the ice cube is in the glass of water, it's displacing a certain amount of water. And when it melts, it replaces the displaced water.
Yes, very good. The displaced, right now the ice cube is floating, right? It's very important, it's floating, which means the weight of the ice cube is equal to the water it's being displaced. So when the ice cube melts and melt into water, it just becomes, let's say you have an ice cube that is 10 grams. Let's make it, 10 grams, for example. That is displacing a weight of the water is also 10 grams. The buoyant force is supporting the ice cube pointing upward. So when you displace it, it's going to exactly become that little bit water that is now occupied by the ice cube. Now it becomes the water occupied by themselves, so that the level of the water will not change. There's a chain of logic is like this. First, you have to use the forced equilibrium because ice cube is floating. So the amount of the weight is equal to the buoyant force. And then you use the Archimedes principle. The buoyant force is equal to the weight of the liquid displaced. So you can say the weight of the water displaced is equal to the weight of the ice cube. So when ice cube melts, it becomes water with the same weight. So the well water takes the place of the displaced water, and the water level will not change. So let's look at another question. Maybe we have time to finish this one before the end of this class. Here we have a tub of water with water filled all the way up. And you have a second case where you have top of the water, but you put a ship on it. So the tub would full and you put a ship in it, okay, and water spills as you put the ship in it. So in these two cases, which one weighs more? I'm gonna let you vote on this. Okay, let's run the clock for 10 more seconds. All right, let me go ahead and stop this. Okay, very good. I'm glad that we see that just by putting the water ship in, yes, you added the weight of the ship, but at the same time, you're also displacing a lot of water. And the amount of water, the weight you displace is equal to the weight of the ship. So you're replacing, let's say, 1,000 pounds of water with 1,000 pounds of the ship, because the ship is staying afloat. So if the ship is 1,000 pounds, which means the buoyant force is 1,000 pounds. If the buoyant force is 1,000 pounds, meaning the amount of water you displace is also 1,000 pounds. So if you put these two on the scale, they're going to weigh exactly the same. But important thing is the tub is filled with water and the displaced water all spills away, right? Obviously, if you have still a lot of room in the tub and you put in the ship, obviously that one will weigh heavier. So there's a little subtlety there. The answer is, the answer is C. All right, so we're gonna stop here today. We're trying to finish our discussion for the fluids on Thursday. And I will send an announcement regarding office hours, and also I'll fix that post-assessment on Blackboard as soon as possible. All right, have a nice day. I'll see you guys on Thursday.
Thank you, Professor. Have a good day.
Thank you, bye-bye, you too.
Thank you, Professor. Have a great week.
Yeah, the bots know how to do it.
Thank you.